short introduction from my side. My name is Oertel. I'm product manager at Draeger Safety and taking care for electrochemical and catalytic bead sensors for flammable gases and vapors, and as well toxic gases and oxygen. And as said, thank you for the invitation to give you a short introduction to use gas detection as measure for primary explosion protection. My focus would be on hydrogen, but the things and rules which I mention here are also applying for other gases as well, like ammonia or methanol, what we heard. The presentation, as mentioned, will be shared, so feel free to use this. Before we start, short introduction to hydrogens, because we need to look what is specific for hydrogen. Hydrogen, we heard it before, is one of the smallest existing molecules. It's flammable, it's non-toxic, it's non-corrosive, so this is good for the industry to handle. It's colorless, odorless, so you will not see it, you will not smell it. So this makes the gas a little bit dangerous because you don't see or smell the risk of the gas. It's the lightest gas what we have, so it will immediately vaporize and rise up. And when we compare this with the typical fuels what we use, like methane, the density is a tenth of it. So all measures what you have in place, or you think about of existing gas like methane, propane, you need to consider now that hydrogen is much more lighter. What is good is when we talk about explosion protection, it has a similar ignition temperature compared to methane. Methane has about 540 degrees, hydrogen 585. So if you select equipments according to the temperature class, this would be very close to it. When we look for explosion protection measures, we always need to look for the lower explosion limits. And methane, depending on if you go for the European or the ISC measures, then it's 4.4 or 5 volume percent. Nevertheless, it's very close to the 4 volume percent of hydrogen. What it makes more dangerous is the bandwidth where hydrogen is explosive, and this goes up to 77 volume percent. So we have a great area which we need to consider with protective measures compared to methane, where we have only 14 volume percent, which is smaller. What is making hydrogen more dangerous is the ignition energy. We heard already about the 0.02 millijoule, which is quite low. So it's not the temperature which makes the ignition dangerous of hydrogen, it's the spark which you can create and which will then ignite an explosive atmosphere. And this is, methane has 10 times more or requires 10 times more energy to be ignited. So this makes hydrogen more dangerous. And this leads to the fact that hydrogen is in the explosion group 2C. We heard this already. So comparing about existing infrastructures for methane or other gases where we normally have 2A or 2B, hydrogen requires 2C. So this means if you look for equipments to be installed in hydrogen application, you need to consider now the different or higher requirement on explosion groups, and as well the greater area of the bandwidth where we can have an explosion. Okay, let's go further on. What kind of standards are relevant for explosion protection? We heard already about all the different steps and the complete supply chain from producing or generating of hydrogen to supply and handling it to the end user, then different standards for the different steps in the chain, and also depending on where you are in the world. My focus is on the ISC world, as this, I would say, covers most of the world as well. This standards from the ISC and in Europe, the EN, are harmonized. That means if you are familiar with the ISC standards, it makes you the access to the European market more easy, because the ISC and EN are mostly harmonized. That means you will find the same contents, the same requirements, and also in other countries which are all ISC members. I split the standards in two sides. So the one side is the employee, so who is dealing with the gases, the vapors, with the risk of an explosive atmosphere, which is on the left-hand side. And we have the manufacturer of equipment, especially for gas detection, which is on the right-hand side. So when I start with the right-hand side, every time when we speak about equipment for explosion protection, we have to fulfill what we heard already, the EN 60070-0, where we find general requirements. Here we will find information about how the marking should be on equipment, so be accordingly the requirements. Then we have different protection concepts like flame-proof enclosures, increased safety, intrinsic safe. So there are a lot of more principles to design a product that it's designed to be used in a hazardous atmosphere. Important for gas detectors is, beside that the device is not being a source of ignition, we need also to define what is the performance of the detector, because we want to use these detectors to detect gases and vapors, and therefore we have standards which define the performance. When we look for the flammable gases and vapors, we have the 29-1 for point detectors and the 29-4 for line of sight detectors. Besides this, we have also standards for the measurement of oxygen, but as well of toxic gases, as we have also here ammonia mentioned. Ammonia is as well very toxic, small concentration you can smell, but as soon we have 100, 200 ppm, you will lose the sense of smelling it, and it gets very toxic and dangerous. So for this purpose, there are also standards defining the performance on toxic gas detectors, which are the 62990 standard. So if you want to use gas detectors for explosion protection on the side of the manufacturer of devices, but also of equipment, you always need to have a closer look to these standards on the right side, and there are some more. If you are an employee, so you need to deal with gases, you have a plant, you're a transporter, some in this direction. We have different standards like the 10-1 and 10-2, especially 10-1. So we need, as we had in the previous presentation, part of the job is always to do a risk analysis or a hazardous analysis. So we need to figure out what is the risk, what is the hazard we are dealing with, and a part of this result is then to classify areas which are concerned by this risk. So in the 60079-1 defines then the measures and the steps how to classify the areas from a zone 0 or up to a zone 2. -2 is about combustible dust, which is not applicable for today. We heard already also we need to consider how to install devices in hazardous areas. There's a separate standard. This is the -14 defining the selection, installation, and also the design of systems, electrical systems, which are installed in hazardous areas. As soon you have erected it and it's in operation, you need also on frequently base to inspect them and maintain them, which is defined in the -17. And if you have to fix, repair, or overhaul these, this is defined in the -19. 17 and 19 also contains a checklist in the end, what needs to be inspected, controlled, on which frequency on electrical devices. Nevertheless, if it's a junction box, it's a pump, or it's a gas detector. So these standards are covering the protection concepts which we saw on the right-hand side. As well, if you want to use gas detectors for primary explosion protection, you need also to select or consider the selection, installation, and the use of these. So as we can see on the one side, we have the definition of the areas. We have standards how to install, how to maintain, how to fix, but also how to select gas detectors. And these are always in line with the standards for the manufacturer. I already mentioned we have primary explosion protection. So the idea is always we want to prevent explosive atmosphere. So Because if we have an explosive atmosphere and we have a spark and we have oxygen, then this can lead to an explosion. And the primary task is always to prevent this. One possibility is preventing the gases to leak. So that means we have a closed containment and we secure that the gases will not vaporize to the outside. This is what we call a gas-tight construction. There are different levels on what is gas-tight, and depending on what level you select, you need to add additional levels of measures, like using gas detectors to secure that the system is really tight. The other possibility is to remove the gases quickly by using ventilation. So if you have a production plant, you have a closed room where you have an aperture which is handling gases like hydrogen, like you have an electrolyzer, then the probability could be that it's leaking and the hydrogen as a gas or a liquid would be vaporized to the outside. And one measure could be that you ventilate the room, so you exchange the air and dilute the possible concentration so that there's no possibility that an explosive atmosphere can raise up. To achieve or to support this, the easiest way is to detect the gases quickly and to activate measures. So this is what we always call primary explosion prevention. So that means measures which prevent that an explosive atmosphere will raise up. The second is, we heard this on the standard, is only to use devices which prevent to be an active ignition source. So only X-certified equipment should be used in a hazardous zone. And this is not only for electric equipment, this is also for mechanical equipment relevant to use equipment which is certified accordingly with the correct marking on it for the temperature class, but as well for the explosion groups, which gives you then the possibility to select if the device is correct in this area. And this is part of the dash 14 is the correct connections, so grounding, and as well using, I would say, areas where like a floor is conductive to avoid static charges. The last one is what we would like to see is to prevent or reduce the impacts and the effects of an explosion. But in some cases, you have process where you have an explosive atmosphere, you have active devices which can lead to an explosion. So you need to consider and to design it in a way that if you have an explosion, this will not, or this pressure which will be created will be released in a safe way, and that no workers or people get harmed, or that the you get a propagation of your explosion. So these are always these three pillars what we need to consider for explosion protection, and this is also the sequence we always look at, is the primary, secondary, and tertiary measures. What is the conclusion when you look into the standards is always, if you use gas detection either as portable, transportable, or as fixed, so this is considered as a measure for primary explosion and gives you the possibility to achieve a secure and safe site. I mentioned already that on the primary explosion protection, when we look for explosion protection, we need to differentiate between looking into within an apparatus, so a machine and an installation, and in the surrounding of it. So if we talk about the within the apparatus, then we can concentrate or can monitor the concentration, but only outside the explosion limits. That means we measure below the low explosion limit or above the upper explosion limit. Within, it's difficult because then you have an explosive atmosphere which is reactive, and this is not concentration monitoring anymore. This is considered as process monitoring. The other possibility is, as for an explosion, you need always an oxidizer. We replace the oxidizer like oxygen by inerting the process. To achieve then a safe process, you need to control and measure the oxygen concentration in the process, which is then, depending on the flammable substance, variant. So that means for methane, you need a different inerting level compared to hydrogen, as the gases have different explosion properties. The other possibility is, okay, if we have a construction we expect which is tight, so we don't want to measure inside, we want only to secure that the installation outside is safe, then we do the prevention in the nearby of the plant or the part of the plant. And as mentioned before, one measure is the leak tightness. So depending how we design a machine and apparatus like welding or using other connection possibilities, like what we call, this is constructive. So a welded connection is always considered as leak tight, and this is a constructive measure. If we use ceilings or we have valves, then these are we need to combine with other measures, and this could be organizational, like using a portable gas detector and do inspection on frequently intervals, or using a stationary gas warning device which is permanently installed there with warning function. So if we have installation, and this could be like an electrolyzer, where we expect that certain connections could leak, then depending on how the electrolyzer is used, we can improve and secure the level by using either portable or fixed gas detectors. Another possibility is if we have these equipment installed under or in the not in the building but outside, then we have a permanent ventilation. So that means even if the system is leaking, which is not good for the environment, and also it will cost the owner money, we will secure by this that the concentration which is released will be all the time diluted. If we have a closed building, then we can also use openings to the room or using technical ventilation to secure that the concentration will not raise up. And this is then considered as preventive or as primary explosion protection. For this, we can use gas detectors to measure all the time the actual concentration and to secure that it will not raise to a dangerous level. Important to consider is always there's an EN standard, it's the 1127. So even if we have a machine which could be leaking, the question is, what is the quantity, what is released? So if the quantity which is released is so small, then no special protective measures are not necessary. Then we don't consider this as an hazardous area, so there's no meaning of doing protective measures. Yeah. Talking about gas warning devices, there are 3 different types of gas warning devices, or how you can use this. The first is gas warning systems just with alarms. So you have a transmitter which is connected to a control system. If the transmitter detects a gas concentration, it will provide a signal to the controller, and the controller will just switch an alarms like a sounder or like a light. This is then depending on the next step of the employee, how to handle these. So what are the organizational measures in this case? The second level is gas warning devices with automatic switching function. That means, again, we have a detection of a gas concentration, we have an activation, but besides giving an alarm, we also activate, for example, a ventilator to dilute the room, so to bring the gas concentration on a safe level, or by switching a valve. The last option is using the gas detection system for emergency function. That means we switch off the complete production. Yeah, that means everything what is not safety related will be deactivated, will be de-energized to secure that the plant is in a safe state. These are the 3 levels how you can use gas detection systems or detectors, and depending on how you want to use it, you need to define measures, and you need also to check if these measures are effective. For example, if you use a ventilation system, you need to secure that also that this ventilation is sufficient to dilute the gas or the possible leak to a level that it's safe. Looking to because the the selection of devices and as well the measures always are in combination with the areas where you want to use it. We have, and I mentioned this before, there's a standard, which is the EN or IEC 60079-10-1 for classifying of areas where dangerous quantities, and here we are talking about dangerous quantities and concentration of flammable gases, how to classify and define the areas where you want to use and you need to work. And there's a special annex just for hydrogen. So there's, I would say, a general description about ventilation, probabilities, etc. But especially on hydrogen is an annex because hydrogen has some properties, as we heard before, which we need to consider. And like it's from the density, it's very light and it will rise up. So you need to consider if you have, for example, installation inside, possible overhead spaces or possible pockets where the hydrogen can be collected. So if you have a closed room and you maybe have on between your roof an overhead area, the hydrogen, as it is the smallest molecule and is very light, it will creep through all the elements until it comes to a level where it can't further on. So it means if you want to define a zone and also to think about positioning a gas detector, you need always to consider the design of the area and the room where the gas could be released. The next point is, beside how the room is designed, you need also to consider how the hydrogen is released. So if it's pressurized, you will have a jet from the point in, depending on how the piping or the construction is, and depending how your room ventilated is, you will have a gas plumb which will go from the side and then upwards. If you handle hydrogen as a liquid and it will leak, then it will vaporize over the time and will go up. So here are good hints, information, what you need to consider when you define or classify the area related to hydrogen, but it gives you already information where to place possible gas detectors in the room where you handle this. Yeah, so here's also under H.8 information about in which direction or what it means if you use vents to ventilate the room. Coming to the point, selecting of gas detectors. So we heard about how dangerous hydrogen is compared to other gases, which standards do we have, about the classification of areas, and in general about gas detection. We need now to look on, okay, which technologies can we use and which are safe to detect flammable gases. And for this, we have this 29-2. This is for the user to select the right detectors, and only technologies which are performance approved, so where we know how reliable these technologies are considered in this standard. So for the flammable gases and vapors, we have different technologies like catalytic sensors, thermal conductivity, IR, etc. So this is always about the concentration in a low explosion limit. Only a few of these can be used for volume percent concentration. And one of the measures is always, if you reduce the oxygen concentration, we can also make a safe area. So we need also sensor technologies to measure the oxygen concentration. And that's why I mentioned this before. There are also alternative technologies which can be used, like ultrasonic gas leak detectors, infrared gas cameras, etc. But these are not, I would say, there are no metrological standards which define and can judge on the performance of these technologies, and therefore they can only be considered supplementary measurement technologies. So it means if you want to do primary explosion protection, you need to consider these technologies, and you can add others to make a safe application. But these technologies here can't replace the standard technologies. To give you a short insight into two principles is electrochemical sensors which is very common to be used for mostly toxic gas, but also for oxygen. These sensors work like a battery. So you have the gases, they vaporize through a membrane into the sensor. Inside you have electrodes, you have electrolyte, you have a chemical reaction inside of these. And what is important for these is always, we are always talking about an oxidation or reduction of gases. That means, like here, CO is reacting with the electrolyte or with the water part of the electrolyte, and we create hydro ions and electrons. And these ions and electrons are used to measure the concentration. So we are measuring always with electrochemical sensors a reaction product. We are never measuring the direct gas. So it's always a reaction and at the electrodes creating electrons, and the amount of electrons is a direct or proportional indication of the gas concentration. As we have different gases which have similar structures, they can lead also to similar reaction and give us a reading. That's what we call cross sensitivity. So if you have a CO sensor, this sensor would be also cross sensitive to hydrogen, depending on how you use the sensor. So in the end, you will see a signal based on the created electrons, and you always need to consider possible what we call interferences based on the cross sensitivity. Another thing is, you can see in the chemical reaction, we need always oxygen. So sensors which are electrochemical always need a certain amount of oxygen in the process or the environment, otherwise the reaction will stop and they will not create any kind of signal. So important is that we can't use them in an oxygen-free environment. Shortly, but then the reaction will stop inside. What is also important is we have inside a liquid electrolyte. There are different ones, so from sulfur acid over different salt liquids, etc. But they are always consisting, a part of it is water, and that's why these sensors cannot be used, I would say, at absolute dry atmosphere or in the atmosphere where we have condensing effects. So you will find always limitation on the parameters where or under which environmental condition you can use these. Because if this goes down to 0 relative humidity, the sensor will dry out and the reaction inside is not possible because the electrons can't go from one side to the other. If it's condensating, then the volume inside will go up and the sensor will break. So you see there are certain effects from the environment we need to consider if we talk about electrochemistry. And as well, high temperature is also, or low temperature is always influencing the performance of the sensor. You know this from, for example, your mobile phone. If you have very cool conditions, the runtime of a battery will go down immediately. Second principle, what we can use for gas detection is catalytic beat. So we use the effect that flammable gases, vapors, can oxidize, so we can burn them. And what we do is we have what we call an not a membrane. What we have here is an sinter disc, or a disc which secures that the gas can go through it, but if we have inside an explosion or fire, these will not ignite through. Yeah, so it's a barrier here inside. What we use is the effect flammable gases like methane or hydrogen vaporize inside together with ambient condition with oxygen. We oxidize these to CO2, to water, and what we have is heat of reaction, because as we convert this, there's always a heat up, and this heat up we measure. How we do this? We have two elements. One element is active, the other is passive. The active is a platinum wire which we heat up to 400 degrees Celsius. We have a kind of material around which is a catalyst to make the reaction possible. The flammable gases will react with the pearl, will convert and will heat up the wire. The other, which is the passive one, is our compensator, and we compare the change of the resistance between the poles by a wood-staunch bridge, and the temperature increase is a direct indicator or proportional indicator of the amount of reaction or of gas concentration inside the sensor. So what we measure is, instead of a gas, we measure the increase of temperature, and this gives us an indication of the gas concentration. As this sensor doesn't know which gas is now present, and we learned that, for example, hydrogen needs less energy for igniting compared to methane, and also from the chemical structure, you see that depending how complex the structure is, you get less heat of reaction. That leads to the effect that different substances give different signals, so less or higher sensitivity. Yeah, so in the end, the sensor will burn or convert all flammable substances. But if these are mixtures, you will never get, I would say, one line. It's depending on which substance you have. Important again to mention is here we need oxygen, so it's a process which is oxidizing. So this principle can't be used in an inert atmosphere. So we need about 10 to 12 volume% of oxygen, otherwise this is not possible. So, and that's why the principle can only be used in the lower explosion limit and not in upper ranges. Important is if you use or you have an atmosphere where the concentration is higher than the lower explosion limit, you won't get a signal which is linear anymore. It will turn down. So you get an indication showing you a lower concentration as expected, which is dangerous. That's why when you have a catalytic bead sensor and the measuring range is 100% LEL, you need to use what we call an alarm which needs to be latching. So it must be designed in a way that the sensor must be checked before we reactivate the sensor for usage. A few things what we need to consider always, and especially on catalytic bead, is if we have high concentration. High means a gas which or concentration which is higher than the defined measuring range, means that the gas is not only outside, it is also inside of the sensor. And the sensor, as we have with the electrochemical, but also with the catalytic bead sensors, principles which consume the gas, it takes time for recovering. Yeah, so an overexposure, how we call this, will always lead to recovery times, and this really depends on how high the concentration was. Alarms, you need to define alarm levels, because depending on the measures you want to use, but also on the risk of the different gases, you want to be alarmed at an early level, but you don't want to get false alarms. So preventing false alarms means you shouldn't go too low with your alarm thresholds to avoid false alarms. Yeah, poisoning is also something, as we have systems, especially on the catalytic bead sensor, which converts a gas a vapor. And some of these gases, like which are hydrocarbon, they just mostly create CO2. But if you have a combination which includes silicon, sulfur, this will also create reaction products, which likes to go to the hottest area. So they will, over the time, react with the pellister or with the pearl of the sensor and will cover this, and this will then over the time reduce the sensitivity of the sensor, and this means that the sensor takes longer to respond or will get insensitive. That's why the sensor elements needs to be checked on a frequently basis. So we recommend every 6 months to check a sensor, referring the sensitivity, and if needed, to calibrate these. And it's not only to check the sensor, it's also to check the complete safety line. That means to see if your measures like alarming or ventilation is also working. In the beginning, I mentioned the performance standards to judge on how good or is the sensor appropriate to be used. We have for the flammable gases the 29-1. So that means when we design a system consisting of a gas detector together with a control unit, we have on the one side the requirements for the explosion protection, so for the secondary, but also when we want to use it for primary, on judging on the performance. That means the detector needs to be not only marked that it's can be used in hazardous area, you need also a type certificate that the judge on the performance of the detector or the transmitter. And as you use the sensor not alone, you use it with a control system. Also, your control system needs to be type certificate. That means because you get signals and you need to be sure that the signals are used or interpreted in the correct way, you need also a judgment or a type certificate on control system. It's not necessary that device or detector and control system are from the same supplier. Important is that these systems are get a conformity certificate, like from the TÜV Nord, according to the relevant standards, that these can be used for this. Yeah, so you need from an notified body a certification on, besides the explosion protection, you need also on the measuring performance of the sensor, but also on the control unit. And this could be like here, this is from the DEKRA. For products what we offer, for example, we have different catalytic bead sensors in combination with different detectors, because it's always the complete system. And in the certificate, you will find the substances to these or for what these detector was tested. So it's not only that you test a sensor, you need also to test the sensor with the transmitter for the different substances and as well for different concentrations. So it's different if you measure a volume percent, or if you're looking for ppm, or you're looking for explosion limits. So in the certificate, you will always find the substances and as well the concentration for what the detector was tested and certified. Yeah, this was a short introduction from my side about explosion protection, primary explosion protection, how to use gas detectors, how they can support you in this, and what is relevant and important to be considered when you use or when you are dealing with hydrogen